Alright, at 6.3 we're really still doing optimization, but we're doing optimization on very specific business and economic related topics. And I'm going a little bit out of order with the textbook here because this is actually my favorite application. So we'll jump straight into this. It's a standard supply chain type problem. And here's what we want to do. We want to manufacture a good. Well, there's a problem with manufacturing lots of goods. It's that if you manufacture a whole bunch of goods all at once, so if you manufacture in very large batches, then you have to pay large storage fees to store all those goods while you sell them, right? If you produce 1 million batteries, well, they have to be stored somewhere while you sell them over time. And if you have 1 million batteries lying around, you have to pay large storage costs to store those batteries. So the solution, you might say, is, well, let's not manufacture 1 million at a time, let's only do 10 at a time. Well, the problem there is, okay, you produce 10, you sell those 10, but every time you go back to the factory and you say, produce me another 10 batteries, they're going to charge you these setup costs, right? You're going to be charged to set up that factory from producing whatever they were producing before back to producing your batteries now, right? So there's these setup costs that come with manufacturing small batches. You really only want to pay these setup costs once and then produce all your goods, as opposed to paying setup costs over and over and over again. But the problem with producing all your goods all at once is, again, this problem of the storage fees. So the question is, what's the economic lot size, quote unquote economic lot size? That is, what's the optimum batch size? How many batteries should you produce at once to minimize your total production costs? Well, this comes under a whole bunch of assumptions, so we'll set up the solution under various assumptions. And let's see, let me just introduce some variables here. So we'll say, let's let Q be the number of units we produce in each batch. So number of units produced per batch. And now I'm going to try and write down a function for my total production cost per year. And the question is, it'll be a function of Q. The question is, what value for Q minimizes my total production costs? So let's say T of Q. This will be my total annual production costs. We're going to try and come up with a function for T of Q. And the question is, again, what value for Q minimizes it, right? What's the economic lot size that will minimize this? Well, what's my total annual production cost? My total annual production cost would be, let's see, I'm going to break this up in several stages. It's the manufacturing cost plus the storage costs. Just at its most basic level. Hopefully we can all agree on that. Our total annual production cost would be the cost of producing all the goods plus the cost of storing all the goods. And as we've seen, the storage costs will go up and down depending on what our batch size is, how many we have to store at any given moment. And our manufacturing costs will go up and down depending on our batch size. The manufacturing cost goes up if we have very small batches because we have to pay these setup fees all the time, over and over and over again. So let's see if we can make this a little bit finer. What are our manufacturing costs? Well, the manufacturing costs would be the number of batches that we produce per year times the cost per batch. Cost per batch. And this will be plus the storage costs. So made that just a little bit finer there so we can think about how we're going to express these things. The manufacturing cost is the number of batches we produce times the cost per batch. And now I'm going to start writing this in terms of variables. So let me make a little bit more space. And I'll introduce a few variables here. So let's see, we'll let, we've already said Q is the number of units produced per batch. K, let K be the cost of storing 1 unit per year. Let's say 1 unit for 1 year. A little bit more precise language there. 1 unit for 1 year. F, lowercase f, is the fixed setup cost to manufacture. So every time you want to produce a batch, this is the cost you've got to pay to your factory to set up to manufacture your good again. G is your cost to manufacture 1 unit, and capital M will be our total number of units, produced annually. Okay, so I want to come down here to this function T of Q. I haven't introduced any variables yet, but we've broken it down into these granular pieces. Our total annual production cost per year, well, I suppose that's redundant, total annual production cost would be the number of batches per year times the cost per batch times the storage costs. So, what are these things? Number of batches per year. Well, I think I can express this in terms of things up here. We're producing M total, right? We're producing M total units per year, and we're producing Q units per batch, so M over Q is in fact this expression. That will be the number of batches per year, right? If you're producing 10,000 units per year and 1,000 units per batch, 10,000 over 1,000 would be 10 total batches. So M over Q is the number of batches per year. The cost per batch is what? Well, we've got Q units per batch, and it costs G dollars to manufacture 1 unit. So this would be G times Q. Right? Q units times the cost to manufacture a unit is almost the cost per batch, but plus this setup fee, plus F. So GQ plus F. That's our cost per batch. Right, again, so pause the video here and think about this for a moment if you want to, but the cost it's going to cost you per batch is 1, the setup fee, and 2, the price per unit times the number of units you're producing. So GQ. Now this one, where we're going to brush some stuff under the rug here, but what's the storage costs? Well, here's what I claim it is. It's K. K is the cost of storing 1 unit for 1 year, times however many units I'm storing. And here's my claim. If I look at how many units I'm storing ever at one time, let's say at a time t equals 0, I produce Q units, right? Q units per batch. I have to store all of those, but slowly over time, assuming I sell at a linear rate, they reduce to 0 until I produce again. Right? I produce Q more units, I have to store them, and then linearly we'll assume they reduce to 0. So the observation here is that at any given moment in time, on average, I'm storing half of a batch. Right? At any moment in time, on average, if you just choose an average moment in time, on average I'm storing half of a batch. So what I can do is I can assume that my storage costs are the cost of storing 1 unit times Q over 2, half of 1 batch. Awesome. And I'm just going to clean this up a little bit, I think. So T of Q is, let's clean this up a little bit. How do I want to write this? I'm going to distribute this the opposite way of the way I've written it. I'm going to have F times M over Q. So a little F times M over Q. Plus M times GQ over Q. The Q's cancel and I've just got G times M. And plus, alright, this is KQ over 2. So a lot went into that. Quite a few assumptions, but accordingly, this is our total annual production cost based on our lot size Q. And you can see what's happening here, right? If I've got two competing pieces, my total annual production cost goes up as Q gets larger, as my batch size gets larger, because of this expression here. There's my storage costs. And as Q gets larger, my total annual production costs go down over here because I'm dividing by a larger value for Q. And this is my setup cost for the factory. So what do we want to do? We want to minimize this. How do we minimize? We take the derivative and look for critical numbers, right? So take the derivative, T prime of Q. We'll just box it off for now. That's important. T prime of Q. We'll differentiate it. Remember, our variable here is Q. You can think of these as being fixed constants. F, M, G, M, K, those are all fixed constants that are determined by the problem at hand. The factory fixes the setup costs. G is fixed, the cost to manufacture one unit. So the variable is Q. We're differentiating with respect to Q. What do we have? Fm, easiest way to differentiate this, think of this as Fm times Q to the minus 1. So Fm times Q to the minus 1, when I differentiate that, I'm going to have minus Fm times Q to the minus 2, or over Q squared, plus derivative of Gm. These are constants, right? There's no Q's in here. Derivative of that goes to 0, that goes away. And derivative of K over 2 times Q, K over 2 is a constant, times Q is just K over 2. Okay, so we'll set this equal to 0 because we're looking for critical numbers. Notice, by the way, technically it's undefined. It's undefined when Q is 0, but that's not in the domain of the original function. We can't produce, well, what did Q represent? It represents the number of units per batch, right? Clearly, we're not going to produce 0 units per batch. That doesn't make any sense. So we're not worried about dividing by 0 here. But if we set it equal to 0, then what do we have? We've got, I'm going to multiply both sides by minus 1 and move the K over 2 over. So this is Fm over Q squared equals K over 2. I probably should have just erased this and gone down. Let's do that. I don't need this anymore. So Fm over Q squared equals K over 2. Multiply both sides by Q squared. So Fm equals Q squared K over 2. We'll divide both sides by K, multiply both sides by 2. So Q squared equals 2 Fm over K. And lastly, that means Q is the square root of 2 times F over M, or sorry, 2 times F M all over K. And my claim is that this is only a critical number. That's all we've shown so far. That's when the derivative is 0. But my claim is that this indeed minimizes total annual production costs. So, we've answered this question under the assumptions that we made, right? The question was, okay, I have this function for total annual production costs. What batch size, what value for Q will minimize our production costs? And the answer is, well, we went through with this function and we found that the answer was Q is the square root of 2Fm over K. There is a catch though. The catch is this formula we came up with, T of Q. This function depended on certain assumptions. For starters, you'll notice that I assumed that there's some cost for storing 1 unit per 1 year. That's not often the case, right? Whether you want to store 1 unit or 1,000 units, you generally have to rent an entire, well, you might have to rent an entire warehouse, right? So whether you store 1 unit or 1,000 units, it might not matter, right? You might be paying the same flat fee either way. What else might happen? We assume that the rate we sold our goods was linear, so we on average stored half of our units at half of our batch at any given time. That might not happen. So there's several assumptions that I made here, and the point I want to make is that this formula for Q that minimizes our production costs only works under these specific assumptions that we made for this formula. What you'll see for homework is you'll see 1 or 2 problems where you have to make different assumptions. You have to make different assumptions on your own and come up with a slightly different formula for T, for your total annual production costs. And then you'll differentiate that and find a different formula for Q that minimizes your total annual production costs. And you'll see other simple problems where you don't have to do that, where you just use this formula straight away, which is an example we'll do right now. The other thing I want to point out is that this is a square root. What does that mean? This is not necessarily an integer. It's not necessarily a whole number. So suppose you plug in all of your information, you plug this in, you get Q is 2.5. Well, clearly I can't produce 2.5 units of a good per batch, right? So the question is, do I produce 2 or do I produce 3? And the answer, the way you determine which one it is you plug them both in. You plug in 2 units into this function, you plug in 3 units into this function, and you choose the smaller one. Okay, so if it isn't an integer value, you have to check. You have to check both sides. Take both whole numbers on either side, both integers on either side of that decimal value, and plug them into this function t, and decide which one gives you the smaller cost. So here's a classic problem. We want to produce 100,000 lamps annually. We're told it costs $1 to store 1 lamp for 1 year, and it costs $100 to set up the factory to produce a batch of lamps. These numbers probably aren't realistic, but bear with me. So it costs $100 to set up the factory to produce a batch of lamps, and the question is, find the economic lot size, find the optimal number of lamps to produce in each batch. So the first thing you should ask is, 1, can I just straight up use that formula we just had? And the answer is, yeah, this doesn't violate any of the assumptions we made to derive that formula, right? We've got a flat storage cost per unit per year. We've got a flat setup cost for our factory, and yeah, it looks like it's entirely within the realm of the formula we just set up. So we don't have to set up a new total annual production cost formula here. So we can just go straight into it. We can recall, okay, Q, the economic lot size, is the square root of 2Fm over K. So what are these things? Well, what's capital M? Go back and then recall capital M is the number of units we want to produce per year. So that's 100,000. What's F? What's little f? Little f, oops, my numbers are going to be off here because I didn't copy this quite correctly. It's going to cost us $500 to set up the factory. There we go. Okay, so little f is the factory setup cost. This is going to be 500. And K is our cost to store 1 unit per year. K is the cost to store 1 unit per year. It's $1. That's all we need, right? We need this formula, and we need to plug in the appropriate values. So as long as you can use this formula, these problems aren't particularly difficult. You just have to know the formula. Q is square root of 2Fm over K, and now we'll plug them in. So Q is going to be the square root of 2 times 500 times 100,000 all over 1. And if you want, plug it into a calculator, you'll get out a number. Hopefully it's a whole number. If it's not, remember you have to check the numbers on either side to figure out which one actually minimizes your production costs. But I don't have a calculator on hand, so we'll just we'll keep going here. What do I have? 2 times 500 is 1,000. This is 1,000 times 100,000. That is, it's a lot easier to take square roots of exponents, so that's 10 cubed times 10 to the 5th. So that's square root of 10 to the 8th. Think of that as 10 to the 8 to the power of 1/2, that's 10 to the 4th. Or Q is 1,000 laps, or 1,000 laps per batch is actually optimal. So you're going to be producing 100 batches. Apparently the setup costs here, $500 per setup, is low enough that you're willing to, oops. 10 to the 4th, this is not 1,000, that's 10 cubed, that's 10,000. That sounds much more reasonable. Okay, so you're only going to produce 10 batches per year, which is much more reasonable. You wouldn't want to pay the $500 setup cost 100 times. 10 times is more reasonable. So this is the economic lot size. This problem is admittedly on the easier side. One, because I don't have to set up a new formula for Q. I can use the one we've already derived. But I've shown you an example of how to do this. So hopefully, under different assumptions, you can derive a new function for T, and then differentiate that to find the critical numbers and a new economic lot size under some different assumptions. And the other thing that made this easier is this was a whole number. I didn't have to check either number on either side. All right. All right, so our next application is going to be the concept in economics of, oops, okay, I'll use this piece. Concept in economics of the price elasticity of demand. So we'll talk a little bit about what this is. But full disclosure, this isn't really an economics class, so we'll get into the mathematics behind it pretty quickly. But so let's say I've got a function. So let Q be some function f of p, where Q is our demand function. Q is demand at a price P. Alright, so all I'm observing here is that Q is what I'm calling demand, and that's of course a function of price. So here's our definition. The elasticity of demand, sometimes price elasticity of demand, or just elasticity for short. The elasticity of demand is defined in the following way. E is minus P over Q times dQ dP. Okay, so we have a demand function. We have a demand function. It's a function of P. And this is what we're defining. Elasticity of demand is defined the following way. It's minus P, the price, over Q, the demand, which is a function of P, times the derivative of Q with respect to P. So Q prime, if you want, the derivative of Q with respect to P. And in this form, this is sort of the final form after you go through a whole bunch of manipulation of what you originally started with trying to measure. This is the final cleaned up form. The problem is, written in this form, it's not entirely clear what this expression E is actually giving you. So I'll tell you what this is doing. This essentially measures the relative change in demand measures the relative change in demand per change in price. Alright, so this is what this equation is trying to do. In this final form, this manipulated, cleaned up form, it's not entirely clear that this is what it's doing, but it's giving you the relative change in demand per your change in price. And what I mean by that is, if you change your price by 1%, say I increase my price by 1%, the question is, how much is my demand going to drop? Is it going to drop 10% or 40%? And that, of course, differs per type of good, right? Something like milk, if you look at the elasticity of milk, it's very inelastic. If you change the price of milk by a little bit, the demand doesn't change very much. Meanwhile, if you take a luxury good, like some sort of luxury car, if you increase the price on a luxury car by even a small amount, the demand tends to change pretty radically. Those are highly elastic goods. So I'll make these definitions now. Demand is inelastic if E is less than 1. So this is how we formally define inelastic goods. Demand is elastic if E is bigger than 1. And there's a very important case here, the case I haven't mentioned, when your elasticity is equal to 1, we say it has unit elasticity. So demand has unit, or sometimes unitary, but unit elasticity if E equals 1. So in a nutshell, this is what elasticity of demand is. It's the relative change in your demand per small change in price. And here's the formula for it. And here's the definitions. Inelastic if E is less than 1, elastic if E is bigger than 1, and unit elasticity if E equals 1. So we'll do an example just using this formula. Okay, so simple question. We've got a demand equation for a new product. It's Q is 200 times e to the minus 0.4p. Again, demand is a function of p, the price. And the question is, find the elasticity, find E, when the price is $100. So we come into our formula. E is minus p over Q. times dq dp, derivative of q with respect to p. And we'll start plugging things in. So we've got minus p, that's just our price, we can't do anything with that. Q, we have our function. Q is 200 e to the minus 0.4 p. Of course, I'm going to clean this up at a later stage. There's no point in writing e to the minus 0.4 p on the bottom here, write it up top if we can. Although I think it'll cancel with our derivative. So times the derivative of q with respect to p. So what's my derivative? Well, I've got a constant times a function of p, so the derivative is going to be 200 times the derivative of this thing. And now we apply the chain rule, right? We've got e to a function of p, so our derivative is going to be e to that exact same function, e to the minus 0.4 p, but times the derivative of the exponent. Derivative of the exponent with respect to p is minus 0.4. So as I expected, some stuff cancels here. 200 cancels with 200. E to the minus 0.4p cancels with e to the minus 0.4p. And the minuses and the minuses cancel. So our elasticity is just 0.4p. So what's our elasticity when p is $100? When p is $100, we have E equals 0.4 times 100 is 40. So this is in fact very, very, very highly elastic. This is very elastic. Right? This says you change the price by 1%, your demand is going to drop by 40%. So it's a very highly elastic good, at least at that price point. All right, so we have another observation to make. So now let's make some observations here. These are super important. What's revenue? Revenue is P times Q, right? Price times demand. So price times demand, or just P times Q. So if I differentiate this, derivative of R with respect to P, technically I'm doing something here called, I think, maybe not. I'm not implicitly differentiating. That'll be our next section. But if I want to differentiate R with respect to P, notice, by the way, this is really a product. Q is not a constant. Q is itself a function of P, right? It's f of P. So to differentiate this, I have to use the product rule. So product rule says it's going to be P times the derivative of the second function, dq dp, plus the derivative of the derivative of the first function, derivative of P with respect to P is just 1, times the second function Q. Okay, so we've got let's see, we've got P times dq dp plus Q. There we go. So there's my derivative. I'm going to write this in a different manner. I'm going to write this in a slightly different form. I'm going to bring this way back here because I need more space. I'm going to just divide top and bottom here by Q. Alright, so this will be Q times P over Q times, no need for brackets there, times dq dp plus Q. Alright, so the Q's cancel and I'm back to my original expression, just P times dq dp. Why did I do that? Well, what is that stuff? That looks a whole lot like E, right? Except E was minus P over Q, dq dp. So this is Q times minus E plus Q. Or if I factor out the Q's, that's Q times minus E plus 1, I'll write the other way around, 1 minus E. So when is this positive? It's positive when E is less than 1. Right, so this means dr dp is positive if E is less than 1. dr dp is negative if E is bigger than 1. 1 minus something bigger than 1 would give me negative. If E is bigger than 1. And dr dp is 0 if E is equal to 1. What am I doing here? Well, that's the rate of change of the revenue. Alright, so that is revenue is 1, it's increasing, right? The derivative of the revenue is positive if my elasticity is less than 1. So revenue is increasing if E is less than 1. 2, it's decreasing if E is bigger than 1. Here's E, there's 1. Over here, we have our function is increasing, our revenue is increasing. To the right of 1, our revenue is decreasing. That means right here at 1, we have maximum revenue. So 3, revenue is maximized if E is equal to 1. There's the end result of everything we just did. The important part that you have to remember is that if you have a demand function, you can find the elasticity, as we just talked about. If you have a demand function, you can find the elasticity. It's minus P over Q times dQ dP. If you want to maximize your revenue, so you don't even have to know a revenue function to maximize the revenue here. If you have a demand function, you can build a revenue function, but you don't have to do that. If you have a demand function, you can maximize your revenue by just asking, when do I have unit elasticity? And that's all you have to do. This is a nice shortcut. So we'll do an example. Okay, so I haven't written many words down here, but here we have a demand function for a good. It's 3600 minus 3p squared. The question is, what price P will maximize our revenue? What price P maximizes revenue? Well, the way we're going to proceed is the way we just talked about. I'm going to find the elasticity of demand. So E is going to be minus P over Q times dQ over dP. So that's minus P over 3600 minus 3p squared times the derivative of Q with respect to P. 0 minus 6p. Okay, so that's minus minus becomes plus. We've got a 6p squared on top over 3600 minus 3p squared. Not a whole lot of simplification I can do with this. I could divide top and bottom by 3 to make it a little bit nicer, but all I'm going to observe now is that revenue maximized. Revenue is maximized when we have unit elasticity. What does that mean? That means I'm going to set this equal to 1, and I'm going to find the value for P that makes it equal to 1. So 6p squared over 3600 minus 3p squared, when do you equal 1? And this is where the algebra comes in, right? There's no more calculus here at all. It's just algebra. I think I pretty clearly want to clear this of fractions, so we'll multiply both sides by the denominator. This means 6p squared is 3600 minus 3p squared. I think I want to group the p squared terms together. So adding 3p squared to both sides, we've got 9p squared is equal to 3600. Divide both sides by 9. P squared is 3600 over 9, should be 400. And that's actually pretty nice, because the square root of 400 is 20. So there's the answer. Just with this demand function, all we have to do is find the elasticity of demand. And we know that our revenue is maximized when we have unit elasticity. So we took our elasticity of demand, set it equal to 1, and found that that happens when P is 20. So this is the answer. 20 indeed maximizes the revenue here. Not necessarily the profit, which is what you care mostly about. I don't know anything about any cost function here, but at least our revenue is maximized when our price point is 20. All right, thanks.